Does anybody have any questions you would like me to go over here? Go ahead. 12? It's a weird question. And I have to be honest with you and say to you, I think if I saw this question for the first time ever in my life, I would be tempted to get it wrong. I think I might. But I know the answer is 90, correct? It's B. Okay. So it's very easy to misthink that and go, oh, I have to double it to get 180, which is what maybe you did or maybe you didn't do. I don't know. But you have 10 different teams and they're going to play basketball games. And when you play a basketball game, you have 2 teams that are playing. What you're told is that each team plays every other team twice, once at home and once at away. So if you think of it with the fundamental counting principle, this is home and this is away. And if you say to yourself, well, I'm going to build a schedule. How many ways can I build a schedule by putting all of the team names in here? Well, this is the fundamental counting principle. There are 10 options for choosing somebody to put in the home position, and there are 9 to put in the away position. And 10 times 9 is 90, and that's it, we're done. And I know that you would be tempted to say, but don't they have to play home and away? Don't I have to flip these? Double it, in other words. And the answer is no, because every time a team that is not your team is playing at home, you have an option of being put here. In fact, you will be put here, right? This includes if the Wildcats. With the Wildcats could be here and any of the other 9 teams there. But any of the other 9 teams could be here, and each time one of the other 9 teams is here, one of these options includes the Wildcats in the away position. So that's going to include all of them. Another more abstract way to look at this, and I don't care for this approach, is to say that since they're playing twice, and I think the playing twice kind of throws you off track, but since they're playing twice, where I put their names depends on the game. Meaning if the Wildcats go here and the Raiders go here, that's a different match than the other way around. Which means order of the arrangements matters, which means 10P2. Which is the other thing we talked about. We formalized the idea of arranging a certain number of items in groups that are smaller than the total amount available in the pool. And if you check out 10, choose 2, you're going to get 90. So if we go to the calculator and just to confirm this, did I just say choose 2? I meant P2. It's pretty significant. 10P2, 10 permute 2 is 90. It's a weird question. I know that you'd be tempted to say, but I have to double it because they're playing home and away, but you don't. Okay. Other questions? Yeah.
11.
Okay, let's look at 11. What do we got going on here? It doesn't matter which one I take it, right?
We only have A.
You only have A. And is A up here the same as your A? Okay. So first of all, if this were a multiple choice or numerical response question, which I highly doubt, you could very easily come to a solution by entering in the left side for y1, x factorial over 84, and the right side for y2. So be very careful and notice how I enter this. I told you when you have that, well, I have one right here, I'll show you. When I have that 10P2, whatever is right next to the N is locked to the NPR, and whatever is right next to the R is locked to the NPR. But if I were to not have this in brackets, well, I'll just show you. If I did this, that's going to take X and subtract 2P2. Okay, that's not what we want. We want to take X minus 2 P2. Okay? And I'm not done yet. I still have, oh, no, not P2. P bracket x minus 4. Does that make sense on how I've entered that? Okay. Now, again, you cannot solve these graphically. You're not going to see some kind of graph with permutations or combinations or any of this stuff. But we can go to my table. I would set up my table to start at, personally, I would start at 4 and go up by 1. Because this n is n minus 4, actually, I cannot have either of those two numbers being negative or 0. We did talk on Friday, I think, about the fact that if you put zeros in some places, you do get answers, but legitimately speaking, they have to be two whole numbers, and the first number has to be more than the second number. That's what's important. So now when I go to my table, all I'm doing is I'm looking for where those things are equal, and they happen to be equal when x is 7. So n equals 7 is the solution. But what if you get this on a written response? Well, I'm going to explore using this formula, NPR equals n factorial over n minus r factorial. I'm going to explore what the right side becomes here, but because I have this n minus 2 and n here, I'm going to rewrite this. And I'm perfectly aware that many of you, maybe most of you, do not need to rewrite it this way. But I'm making it very general here. Because I have n's and r's here and I have n's here, it can be confusing. So what I end up with is n minus 2 factorial on the top. And on the bottom, I end up with n minus 2 minus n minus 4 factorial. And then this is equal to n factorial over 84. So what is, let's deal with the big clunky thing in brackets. What is n minus 2 minus n minus 4? What's 2? And there are a number of ways to do this. Some of you might take that negative 1 in front of the brackets and multiply it through. I would personally just say this n minus this n is 0, and negative 2 minus negative 4 is 2. So now we're left with this. N factorial over 84 is equal to n minus 2 factorial over 2 factorial. And I'm aware, and you're aware, 2 factorial is 2. But I wanted to write 2 factorial because there is a factorial there. We can drop it in a minute. Now, the other day, we were doing stuff like, so this is totally off the road here. This is not this question. But we were doing stuff where we had n factorial over, say, n minus 2 factorial. And we made a big deal of the fact that n minus 2 factorial was a smaller factorial than n factorial. So when we expand out the smaller factorial, pardon me, when we expand out the larger factorial, we should encounter sooner or later the smaller factorial. This n factorial becomes n times n minus 2, pardon me, times n minus 1 times n minus 2 all the way down the line, which means that n minus 2 is n minus 2 factorial. And we canceled those. Well, that's not the only way you can cancel factors. You can cancel factors if they are on top of each other, like one on top of the other, or if they're factors on both sides. So when I expand out this n factorial over here, and by the way, maybe I'll point out to you, we could easily rearrange this so the n minus 2 factorial is on the bottom. Okay? But I'm not going to. This is n times n minus 1 times n minus 2 all the way down the line. This, of course, is n minus 2 factorial. This is over 84, and it's equal to n minus 2 factorial over 2. So I've gone from 2 factorial to 2 there. 2 factorial is 2 times 1, which is 2. So now what happens is I can cancel this n minus 2 factorial with that n minus 2 factorial. Be left with n multiplied by n minus 1 equals 84 over 2. There's a number of ways you can visualize what's going to happen here, but if I kind of half-heartedly cross-multiply by just getting rid of the 84. I get 84 over 2, and now what I have is n squared minus n equals 41. No, 42. Yeah. I've expanded this out, everybody, because I know, looking ahead, that if I did, it would be quadratic, so I need to expand it to zero the equation. This becomes n squared minus n minus 42. And now we're finally in some familiar territory of factoring. The two numbers that multiply to give negative 42 and add to give negative 1 would be these two, negative 7 and 6. But when we solve this, of course, it's Monday, so I just want to make sure that you remember the numbers we found are not the solutions. This leads us to n plus 6 equals 0 and n minus 7 equals 0. This leads us to n is equal to negative 6 and n is equal to 7. But because of the limitations in Math 30-1 about permutations and factorials and all that, n cannot be negative 6. In fact, I would make a point up here of saying n must be greater than or equal to 4. It has to be the value of n that would lead to zeros possibly, but never any negatives for those two subscripts. Yeah.
So we should put equal then also? Because sometimes it can equal 0, but sometimes it can't. We should still put.
Well, yeah, okay, we'll dissect this. This should be equal to 0 because, or equal to 4. Yeah. That's what we're talking about. Because if I put 4 here, I'm going to have 2p0. That makes sense. It doesn't really make a lot of sense, but it means you have two items. How many ways can you arrange none of them? One way. You just did it. You didn't do anything. And by the way, if you take 2p0, you should get 1. I really hope. Okay. Other questions? All right. So we have one more lesson on permutations to go. This is part 3. We're going to continue to look at more restrictions and more, I guess, different kinds of problems than you might have seen. But more importantly, we're looking at repetitions. And repetitions mean you have items that are identical. So for example, if I have 4 quarters and 3 dimes, how many ways can I line them up in a row? I mean, think about that. You have 4 quarters, you have a quarter, a quarter, a quarter, a quarter, a dime, a dime. I think I said 3. If I didn't, I'm going to say 3 now. If you had 4 quarters and 3 dimes, how many ways can you put them in a line? Well, you might say, well, we learned this, that's 7 factorial. But it's not 7 factorial because of those 7 factorial arrangements, one of them would be this, the other one would be this. You can imagine me lining up the 4 quarters and the 3 dimes in that order, and then I go, okay, watch this, I'm going to move the 2 dimes. If I switch the 2 dimes, it's still the same order, isn't it? It's still the same arrangement. So that's what we're talking about. This may be, it could be almost anything. It could be rearranging all of the letters of the word Mississippi. There's a whole bunch of I's that are identical, S's, P's. It could be that I'm going to park 4 pink Austin Minis in a line with 3 blue Rolls Royces, same model of vehicle. It could be that I have, and I'm sticking here with 4 and 3 for this, but I have 4 chocolate chip cookies and I have 3 coconut cookies. How many ways can I eat those cookies? Eat all of the cookies. How many? I could eat chocolate, 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 or I could eat chocolate, coconut, chocolate, coconut. There's lots of different ways. So let's get started here, some review stuff. How many ways can all of the letters of the word oranges be arranged if there are no restrictions? Well, that should be like stealing candy from a baby. There are 2, 4, 6, 7 items in that list, I believe. and that would be 7 factorial, which I seem to recall is 5,040. Thank you. By the way, you can make a mental note here that all of the letters in the word oranges are different. It wouldn't be 5040 if some of the letters were the same. What about if the first letter must be an N? Well, there's a number of ways to do this. One, there's my 7 blanks. One is to say I'm going to go back to the fundamental counting principle and say that that must be an N, and these are open season, which means you can pick any of them anywhere. So there's only one N. The fundamental counting principle says that's the number of choices for that. And then you're down to 6, and then 5, and then 4, and then 3, and then 2, and then 1. Okay? Or you could do what I do in my head. I just say, if the first letter must be an N, the question is asking me how many ways can I arrange these 6 letters? I'm not even going to look at the N. You've already told me. You're not giving me a choice here, so I'm not going to worry about it. And in either case, you're going to get 6 factorial no matter how you look at it. And that is 720. Yeah.
Are we to assume in a question like that you're not allowed to repeat the letters?
Yes. And I'm not just saying yes and turning away. I want to address that. The key word is arranged here. And sometimes we're going to run into situations that are described to you where it's obvious that you can't repeat. And sometimes you're going to run into situations where it's obvious that you were allowed to. Phone numbers, for example. Digits can be repeated, right? Getting cards in a cribbage hand, a card game hand. Those cards cannot be repeated. There's only 2 ace of spades in the deck. But sometimes where it might be ambiguous, if you see the word arranged, that means moving around. So when you physically think of, I'm going to go home, I'm going to rearrange my living room. I don't like where the couch is. I don't get to leave my couch there and put it someplace else. Things get arranged by moving from place to place. Incidentally, you could say, I'm not going to worry about the N. This, I think, is overkill, but you could say, well, that means I have 6 items and I want to arrange them in groups of 6 at a time. All of these are legitimate answers and legitimate strategies. Example 2, how many arrangements of all of the letters of the word brains are possible if the letters B, R, N, and S must be together? And as we're going through this, just make sure to let me know if some of your questions are different than some of mine. I think this lesson is pretty good. This is no different, except for the numbers and the context, than the question that said, how many ways can the 8 volleyball players be in a line when Joan and Emily have to be together? It's the same question, except now with these 1, 2, 3, 4, 5, 6 items, you're not arranging 6, you're arranging these 3. Right? Because if the B, R, N, and S must be together, you really have these 3 items that you're arranging. But we know, I hope we know, that's not the answer because you also have to do something else. It's like Bobby Bear again. Bobby Bear has to put on a pair of pants and a shirt. We have to arrange these 3 things and we have to do something else. What is that thing we have to do, Isaac?
You have to arrange the combination in which you put B, R, N, and S.
Right, I have to arrange the B, R, N, and S. And that's 4 factorial. Now, I just want to make sure you're aware of something here. You used the word combination. I used the word combination earlier by mistake, or choose. We want to not use the word combination whenever we're talking about order, because a combination is something different that we're going to learn about tomorrow. So I don't know what this is going to be. 24 times 6 is 144. Good? Okay, warm up. Arrangements with identical items. So we're going to start off with a very basic question. How many unique arrangements of the 4 letters of the word past are there? Sorry?
We have one more example before.
Do you?
Yeah.
Thank you.
Yeah, that's it.
Oh, I guess I just skipped over it. My mistake. How many arrangements of all of the letters of the word pitcher if the vowels must be together? It's Joan and Emily, right? Except it's not Joan and Emily, it's I and E. The I and the E are one item. The P is an item. What else do we have? The T, the C, the H, and the R. Did I get them all? Okay. So I'm arranging 1, 2, 3, 4, 5. I believe that's 6 items, which would be 6 factorial. But I also have to arrange those 2 items, which is 2 factorial. So I get that, which is, I want to say 1,440. Yes? Okay. Okay. Does anybody remember how we would do B?
Take all of the letters, so I think that would be 7 factorial, and then minus the amount or the number of permutations where I and E are together.
Perfect. When you take 7 factorial, which I think is 5040, you get 5,040 unique arrangements of all of the letters, and some of those arrangements will have the vowels together, and some will not. There's no other option. The vowels are either together or they are not. So if you take away from the total the number where the vowels are together, you're going to get the number where the vowels are not together. 5040 minus that is, I want to say 3,600. 3,600. All right. Any questions with that example? Okay, let's take a look now at the new material. We're arranging items where some of the items are identical. So we're going to start off with the letters from the word past. How many ways can you arrange all 4 letters from the word past? It's 4 factorial, right? It's not a trick question. You can write down 4 factorial, or 4 times 3 times 2 times 1. I have more time on my hands than you, perhaps, so I decided to list them all. Okay, you would never be expected to do this, but there they are. Those are, and you can go through the list. You can see if you can find any more. That's it. I have no life. I've got them there for you. Past, pats. Clearly, these are not all words, right? But they are arrangements. And because they're arrangements, we cannot use the same letter twice. But what if I said to you, how many unique arrangements of the 4 letters, just want to bring something up here. How many unique arrangements are there of the 4 letters of the word pass, which is different than past? What's going to happen is any of these, when you look at the word past and you go to pass, basically what's happened is this T right here, this T changes to an S, doesn't it? So in this list, every single one of these arrangements, wherever there's a T, that T is going to become an S. And that's what I've done. I've taken that same list and I've changed all of the T's to S's. So for example, this word was past. This was P-A-T-S, I believe. This was P-T-A-S or P-S-A-T. I don't remember which one it was, but it doesn't matter. Every single S, we have extra S's because every single T became an S. Are you with me on that? So what happened here? Do we still have 24 arrangements? We don't. Because, for example, we have the word pass here, and someplace else, there's a pass right next to it. And if you think about the reason why, this should make some sense to you. If you think about the reason why, this was P-A-S-T. This was P-A-T-S. If the T becomes an S, then any 2 words where the T and the S's were in the same positions are going to turn into the same word. And for example, you can see this all over the place. There is apts. So the T and the S are in the last two places, and it starts with an A and a P. Is there something else that starts with an A and a P with the T and the S in the same two positions? Yes. So when the T's become S's, those two turn into one arrangement. And if you were to go through here and look at all of the unique arrangements in this list, you could do the following. You could say, well, that doesn't count because we already have it. I have PSAS there and here, so that first one doesn't count. I have a PSSA and a second one, that doesn't count. And that row, that top row, and by the way, that top row is all of the ones that started with P. That top row collapses from 6 to 3, doesn't it? And that's going to happen for all of them. We have, I'll circle the ones we're keeping. We have APS. We don't need that one. We have ASP. We don't need that one. We have ASPS. We don't need that one. SAP. SAP. SPA. I'm going to stop doing that because it's starting to annoy me. SSPA. SAPS. We'll keep this SAPS and get rid of that one. SASP. We'll keep and get rid of this one. SPAs we'll keep and get rid of this one. We'll keep this combination or arrangement rather and get rid of that one. So we get half as many arrangements. The answer to the question is 12. Now, what happens? We went from past to pass. What happens if we go to SAS? So if you take a look at the word here, we're going from past, P-A-S-T, then we have pass, P-A-S-S, and now I'm changing it to SAS, S-A-S-S. Now we have 3 of the items that are identical. Well, I can take this list that I have here, and basically any place there's a P, change it to an S. And I hope you see that it's going to collapse even further. That whole first row becomes SAS, SAS. There's lots of combinations here. For example, we have SAS here. Come on. We don't need that SAS. Are there any other SASs? There's one here. There's one here. We've got SSAS gone. And for goodness sake, you're not going to do it this way, right? There's a shortcut. We have SSA, SSSA. We have AS. Get rid of that, that. SAS, I forgot to get rid of that. We have an SSA, SSSA we got rid of. SAS, I forgot to get rid of that. SSAS we got rid of. SSAS we got rid of. How many are we down to here? 4. And to many of you, how many of you does that make sense that since only one A is there and the rest are S's, the A can be in the first, second, third, or the fourth spot? Okay, so now the question is, and I want to see if you can figure this out, what is it you do to the number of permutations of all 4 letters if all of a sudden you have 4 letters and 2 are identical? How do you go from 24 arrangements to 12?
You divide by 2, and in this case it would be number of duplicates factorial. If you were
Excellent. And some people might just say, well, you divide by 2. But you're dividing by 2 factorial because 2 of these items are identical. This is the rule that's going to work. So if you take 24 divided by 2 factorial, you get 12. This is 24 over 2 factorial. This is, of course, well, can I do this instead? I like that you said 24, and I led you down that path by saying, what do you do to the 24 to get 12? But it's really 4 factorial over 2 factorial, right? And had you not included the 2 factorial, you just said 2, some people might think that this is going to be 4 factorial over 3. And it's not. It's 4 factorial over 3 factorial. You have to divide by 6. And this ultimately brings us to the rule for this lesson, which is that if you have items that are identical, the number of unique arrangements is always found by dividing by the number factorial, where that number is how many identical items you have. So in the case of my 4 chocolate chip cookies and 3 coconut cookies, how many unique ways can I eat them is the same as saying how many ways can I line them up. And we're going to assume that the chocolate chip cookies are like perfect, the same cookies. It's not like one has a whole bunch of extra chocolate. Okay? Well, then it would be 7 factorial, because I'm arranging 7 items, but 4 are identical and 3 are identical. That would be the answer, whatever number that is. And it doesn't matter how many repetitions you have. You could have items that are 4 chocolate chip cookies and 3 coconut cookies, and you could have 5 snickerdoodles, and you could have 8 Oreos. I don't know. And that is the rule you're going to use. So we're going to run through a couple of quick examples here. One is just a very basic example. If you wanted to arrange all of the letters of the word calculus, how can it be done? Now, I'm just going to show you a strategy here because it is interesting that people will get this wrong because they can't visually keep track of all of the items. Okay? They make little mistakes. So what you do, first of all, is you count these. 1, 2, 3, 4, 5, 6, 7, 8. It's 8 factorial. And then you divide by the repetitions. And some people will just look at it and they will get the numbers wrong. Okay? So what you can do is start at the beginning and cross off the C. And your mind is saying C. And you go left to right. You see that there are 2 C's and you're done with them. So there's your 2 factorial on the bottom. Then you go to the A. All right? Well, there's no other A's, so I don't need to worry about that. You go to the L. There's a second L, which is a 2 factorial. You go to the U. There's a second U. It's just a way to keep track of things. And then, of course, we have the S at the end, but there's only one of them. So this is equal to 7 factorial. Does anybody know how I got 7 factorial? What did I do there, Jack?
Because 7 factorial times 8 is 8 factorial, and 2 factorial times 2 factorial times 2 factorial is 8.
Excellent. On the bottom of this, we have 2 factorial times 2 factorial times 2 factorial. Well, 2 factorial is 2. 2 times 2 times 2 is 8. So 8 factorial over 8. And you approached it the other way around. I'm starting at the end. But 8 factorial is 8 times 7 factorial, because it's 8 times 7 times 6, etc. And this is over 8, so we could do that. Any questions with that example? Okay, we don't have much left here. This is a relatively short lesson. You're going to get lots of time to practice many permutations problems today, because tomorrow we're going to move on and look at combinations. Can you just confirm that this is the diagram you see on your next example? Okay. So Jillian is walking from her home to school. This is where she starts. And this is where she finishes. How many different ways can she walk there? Now, there's some conditions. She must always get closer to the school. She cannot dawdle, as my grandma would say. Don't dawdle. She can't do this. That's no good. She must always get closer to school. And what that means is there are 2 different moves. There are only 2 different moves. What are the moves? There they are. She has to, in this diagram, move to the left or to the top of the page. And this is, and I've used this analogy with, I think, with you before, this is the kind of problem that maybe my grade 7 math teacher would give me just to shut me up for a half hour, because you'd have to try to trace them all out, right? And I hope you see the futility of doing that at this level. It's going to be very complicated. So what we're going to do is we're going to label these as letters. This is L and this is U. L for left, U for up. And we're going to recognize that based on this grid, she has to make 4 moves up and 5 moves left. For example, here is a path that she could take. She could start here and do this. And she would be done. She ends up here. Now, what has she done? She has moved left, left, up, left, up, left, up, up, left. Would you agree? So if you asked her, how did you get to school today, and you had this code worked out, you could say, she could say, L, L, U, L, U, L, U, U, L. And that would be an instruction on one way to get to school from home. Right? This is saying go left twice, go up once, left twice, left twice, up one, left, then up, then left, then up, then up, then left. You get my drift here? But if she wanted to, she doesn't have to follow that path. She could take this path. She could do this. Maybe she is just a very linear person. She wants to just get things done. She doesn't want to spend time turning corners. In which case, that would have been an up, 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 left, 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 left. Would you agree? And what I'm getting at is any arrangement of those letters is one of the ways that she could do the job. We're arranging 9 letters. We're arranging L, 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 U, 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 U. We're arranging those 9 items. And every unique arrangement is a unique path. So how many paths there are is the number of ways to arrange those 9 letters, which is 9 factorial over 5 factorial, because 5 of those letters are identical, and over 4 factorial, because 4 of the letters are identical. And that's how we can find out how many pathways there are. I think the actual number is not as important as the strategy here. So before I get a number, does anybody have any questions on that logic? Because this could very well be a numerical response question where the answer is a factorial over b factorial c factorial. Could be something like that. Excuse me. So 9 factorial divided by 5 factorial 4 also divided by 4 factorial. I think we've stumbled across this way of thinking, for me anyway. You could put brackets around the 5 factorial times 4 factorial, or you could just say I have to divide by both. Regardless, the answer is 126. And just if you stop and think of the size of that number, it's not astronomical, but if you tried to trace them all out and keep track of them, I don't think you can do it. I don't think anybody can really do it. I'm sure somebody in the world could, but not me. Any questions with that one? All right, so how many ways can we get from A to B? Is this the same as your diagram? Okay. Well, first of all, to get from A to B, you have to do 2 things. M for middle. I know it's not exactly the middle, but there's a middle point there. You have to go from A to the middle, and you have to go from the middle to B. So what we need to do is find out how many ways to go from A to B, and how many ways to go, A to M, and how many ways to go from M to B, and multiply them. It's Bobby Bear. It's just that it's not as simple as a pair of pants and a shirt. It's more complicated. Because this, which might be a number of pairs of pants for Bobby Bear, this has choices as well. For A to M, you're arranging the following letters. You're arranging R, 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 D, 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 D. Do you know what I'm using R and D for? Right and down. I have to move 3 moves to the right and 4 moves down. And M to B is arranging, bless you, arranging right, right, down, down. And the order that I write those letters down at this point doesn't matter as long as I know how many there are and how many are identical. The word and means multiply, and off we go. 7 factorial over 3 factorial for the 3 rights, 4 factorial for the 4 downs. And I'm going to stop here and just mention, because some people, this has happened in the past, some people at this point go, but they're not identical. Because they'll say, this right is different than this right. And you're correct. But that's not what we're talking about. We're talking about arranging these letters, each arrangement of which gives a unique path. And those letters are the same, R, R, and R. And then we have to go times. This is 4 factorial over 2 factorial, 2 factorial. I'm pretty sure this gives me 6. Is the other one 210? No. 105? What is it? 35? Oh, it's factorial, right? 35. So you end up with 210. And that's it. No matter how complicated the pathways get, that's the most efficient way for you to find the number of different ways that it can happen. And that is it for today. So on page 14, 1 to 5, I think it's page 14. Yep. 1 to 15 rather. And then page 18 is 1 to 7. You do not have to do all of these. When you get to page 18, I think what page 18 is going to be dealing with is the pathways. Page 14 is dealing with repetitions and identical items and just some extra practice. If you're really up for it, you don't have to do any of these if you don't want to, but if you feel the need for practice, page 20, 21, and 22 has just a boatload of permutations problems, okay? So you got about a little less than a half hour to work on this. I'll come around and I'll check on you in just a minute.